let me begin. So welcome to the second part of the workshop tutorial rather on total search problems in economics and computation. Paul gave you a pretty high-level overview in the first part, and now I'm going to go into more technical details. So let me start by listing some PPAD-complete problems. Paul already mentioned some of them. So the most famous one probably is the computation of a Nash equilibrium that I'll just call the Nash problem. So that was proved to be PPAD-complete for a constant number of players, even 2 players. And then there were various follow-up results showing that the hardness result continues to hold even for other types of games, more restricted. So for example, we know that the problem remains hard even if the games are constant rank, meaning that if you add the 2 matrices of the 2 players, you get something that has a constant rank in the linear algebra sense. Then there was a result proving that the hardness result continues to hold even for anonymous games, where a player decides on what to do without caring about who the other players are, essentially, at a very high level. The result was also extended to sparse games, where the matrices of payoffs have very few non-zero entries. And then there was another result that I want to mention, which is, what if you have many players, but the game has a succinct representation? So this is the case for Polymatrix games and graphical games, and we'll see a bit more about this later. So it turns out that these games are, in a certain sense, even harder, namely even getting a constant approximation of a Nash equilibrium is very hard here. So this was kind of the game theory problem. Another more economics like problem is the market equilibrium problem. In this problem, you're given a market, meaning that you have items and buyers who have some money and interested in buying those items. In some settings, they also come with their own items that they can sell. Sometimes they just come with money. And you're interested in finding equilibrium prices, meaning prices where the market clears, everything is sold and everything is bought. And at the same time, everyone believes that they got the best they could get with the money that they have. So there again, there are results proving the existence of such a market equilibrium. And in recent years, there's been results showing that it's actually PPAD-complete to find this equilibrium. And again, this holds for different models of market. There's the Arrow-Debreu, very famous model. There's a simple model, the Fisher market, where the agents just come in with money and they can just buy some items. And even in this simpler model, as soon as you look at not very simple utility functions, you get PPAD completeness. And one final example of a PPAD complete problem I want to mention is a k-cutting problem. So there you have a resource and you want to divide it in such a way that all the agents involved believe that you divided it in a fair way. And for a specific version of this problem with very general preferences, the problem turns out to be PPAD-complete of computing that solution. So in this second session of the tutorial, I want to focus on how do we actually obtain these PPAD hardness results. So I won't have time to talk about PLS hardness, PPA hardness, etc. I'll just focus on PPAD hardness, which is probably the thing we know how to do best, and which is probably the most interesting for this economics and game theory audience. But before we go any further, perhaps we should just pause and think about what does it mean to prove a PPAD completeness result or a PPAD hardness result. Why do we care? Well, it's not only a negative thing, right? If you think about it, proving that some version of a problem is PPAD hard tells you that it's very unlikely that you'll find a polynomial time algorithm. But it also tells you that if you look at some restricted version, it guides you towards a restricted version where you might be able to get a polynomial time algorithm. So in a certain sense, it allows you to stop wasting time on a version of the problem that is perhaps too general to be solved efficiently and helps you find tractable subcases. But wait, I just said that PPAD hardness means we cannot find a polynomial time algorithm. Why do we believe that? So let me just spend one slide on that. What are the reasons to believe that PPAD is different from P? That a problem that is PPAD-complete cannot be solved in polynomial time? And the same arguments and the same answers here, they also apply to PLS. So the first answer I can give to this question is, well, there are many seemingly hard problems that lie in PPAD. So it would be very surprising if you could come up with a problem with an algorithm that solves all the problems in PPAD in polynomial time. Maybe not the best argument, but it does mean something, especially when you have so many problems in PPAD. The second answer you can give, a bit more technical, is that there are oracle separations between the classes. And in the theory of TF and P, for now, there hasn't been an oracle separation that has been proved wrong. So for now, that does mean something. It means that some types of reductions that are kind of black box are not going to work to prove that PPAD is equal to P, or that PPAD is equal to PLS, etc. And the final and perhaps most convincing answer, I would say, is that there are results showing that these classes are hard under some cryptographic assumptions. So what does that mean? Well, it means that if you come up with a polynomial time algorithm for PPAD tomorrow, that will have consequences for cryptography. Namely, it will mean that cryptographers will find out that some things that they thought were secure or possible in cryptography are not possible or not secure. So there are some results in that direction based on more and more realistic cryptographic assumptions, meaning on problems that we believe, that more and more people believe are actually hard. So that's another extra reason. So for now, for the rest of the talk, we're just going to assume that PPAD hard indeed means that the problem is not solvable in polynomial time, and we're just going to focus on how do we show PPAD hardness. So going back to this list of all PPAD-complete problems, if you want to show that one of these problems is PPAD hard, well, the first thing you have to do is you have to define what does that even mean. PPAD hard means that you can reduce from some PPAD-complete problem to your problem of interest. But then again, you have to define what does it mean to reduce? What is a reduction? All right, so what I'll do is I'll start with a refresher about NP hardness, first of all. So what does it mean to prove that a problem is NP hard? So how do we prove NP hardness? Sorry, for some problem A. All right, so we have to come up. Okay, so we have to come up with a with a reduction from 3 set to a problem of interest. And so what does that mean? It means that we have to show that there exists a polynomial time function f that maps instances of 3 set to instances of the problem that we're interested in. And we want the following thing to hold. If some instance x is a yes instance, for 3-SAT. That must be the case if and only if f of x is a yes instance for the problem A that we care about. All right, and the intuition here is if we can solve A in polynomial time, then we can solve the 3-SAT problem in polynomial time. So now let's try to adapt this to PPAD. Paul mentioned earlier in his talk that there is this end-of-line problem, which is the canonical PPAD-complete problem. Now, if you don't remember anything about it, don't worry. We don't need anything about it except the name. I'm very sorry for this. I have COVID, unfortunately. Been at home for the past few days, but I think it will get better in a few minutes. All right, so what I'll do is I'll just take the existing definition for 3-SAT, proving a reduction from 3-SAT, and just replace everything by end of line. And to make things more concrete, I replace the problem A by Nash. Okay, so how do we prove PPAD hardness of Nash? We're going to reduce from a PPAD-complete problem, end of line. And now here I just took the definition of a reduction as it was, and I just replaced 3-SAT by end of line. And now if you take some time to look at this, turns out that there is an issue. Okay, so what is the issue? Well, we're saying, okay, there exists this polynomial time function f, and we want x to be a yes instance for end of line, if and only if f of x is a yes instance for Nash. Now, what's the problem with that? Well, both end of line and Nash, and in fact, all the problems we're going to look at, they're always, all the instances are yes instances for them, because they always have a solution. So this condition is not going to cut it for us. It doesn't mean anything. What that means is that we have to replace it by something that works for us, and by something that actually implements this intuition that we have at the bottom. Namely, if we can solve Nash, then we can solve end of line. So what is that condition going to be? It's going to be, what we want is that this reduction f, this polynomial time function, it ensures that if you give me a solution y to instance f of x of Nash, then I can efficiently, namely in polynomial time, obtain a solution to the instance x of the original end of line problem. Okay, so it's again implementing the original intuition that we want, but the definition is to be modified a little bit to work for these total search problems. I haven't put the fully formal definition here. I think this is enough. Again, you can just remember the intuition. We want to take instances of end of line, turn them into instances of Nash, and then from any solution of Nash, be able to turn them back to a solution of the original end of line problem. Okay, so now let me talk a bit about how these reductions work in a bit more detail. So in essence, we just said, in order to prove that Nash is PPAD hard, you have to reduce from end of line. That is true in essence, but what you actually have to do is to go through quite a few intermediate steps in this reduction. It's not a straightforward reduction. So you start from end of line, you go to discrete Brouwer, which is a discrete version of Brouwer's fixed point theorem. Then you go to a problem that's called the generalized circuit problem. And then finally, you can reduce to Nash. Now, what does that mean? Does that mean that when we have to prove PPAD hardness, we have to go through this whole chain of reductions? No, fortunately, the hard work has been done before. And so now all subsequent work reduces from one of the problems on the right end here, namely either the generalized circuit problem or the Nash problem itself, depending on what problem you're looking at. So in a certain sense, this generalized circuit problem has become like a standard tool for proving PPAD hardness. Now, this is definition of the problem. And normally, I would tell you more about this problem. I have slides for that. But instead, I'm going to tell you about a simpler version of that problem, which is from joint work with Telegas Fernley and Melis-Rugos. So this is a version of the problem that I think is simpler to present, and it also allows us to get stronger results. So I think it's better for this kind of tutorial. So now I'm going to define what this problem is. I'll try to go pretty slowly. I'll make a pause for questions at the end of the definition and after the examples. And then we'll look at an application of how to use this problem to prove an actual hardness result. Okay, that's the roadmap for the rest of the tutorial. All right, so what is this pure circuit problem? Well, we're given in the input a Boolean circuit, but there's a twist, or a few twists actually. So the first one is we allow in this circuit, we allow cycles. So the circuit is not a cyclic, it's allowed to have cycles. The second twist is that the nodes in the circuit, they can take values between 0 and 1, any value between 0 and 1, not just the values 0 and 1 that usually represent, true and false. You actually allow all the continuous values between 0 and 1. And the third twist is that in addition to the standard logical gates that you would find in a standard Boolean circuit, namely NOT, OR, AND gates, you also have a new kind of gate, which is the PURIFY gate. Okay, so the input to the problem is just a Boolean circuit with cycles and with this additional PURIFY gate. And what is the goal? The goal now is to assign a value between 0 and 1 again, not just 0 and 1, any value between 0 and 1, to every node of the circuit, such that every gate in the circuit is satisfied. And I haven't defined what satisfied means yet. I'll do that in the next few slides. But this is the general definition. I give you this circuit, which is essentially a graph with nodes and gates. And I tell you, find me a satisfying assignment of that circuit. So let's take a look at the different gates now. So the simplest gate is the NOT gate. So the NOT gate has one node as input and one node as output. Okay, so the round orange things here are the nodes of the circuit and represent the gate by this green thing. All right, so one input node, one output node. What does a NOT gate usually do in a Boolean circuit? Well, if you give it 0 as input, it outputs the negation, which is 1. If you give it 1 as input, it outputs 0, the negation. That's all that can happen in a standard Boolean circuit. But I mentioned here that in this kind of circuit, we allow any value between 0 and 1, as well as 0 and 1 themselves. So we also have to specify what this NOT gate does, or what it needs to be satisfied if the input is not 0 or 1, but something between 0 and 1. For example, what if the input is 1/2? What does the output of the gate need to be for the gate to be satisfied if its input is 1/2? And the answer is that the gate doesn't care. If its input is 1/2, the output can be anything. And by anything, I mean any number between 0 and 1. Okay, the gate doesn't impose any constraint in that case. In other words, it's happy with any output whatsoever. And this holds for any input that is not 0 or 1. Okay, so one way to think of it is that If the input is a pure bit, namely it's 0 or it's 1, then the NOT gate is going to care about the output. It's going to be satisfied only if the output is the correct computation, namely the negation of the input. But if the input is some non-pure bit, namely some value between 0 and 1 strictly, then the NOT gate is not going to impose any constraint whatsoever. It's going to be fine with any output value whatsoever. Okay, now let's move on to the AND gate. Again, the high-level idea, the philosophy is the same. Let's first go over the pure bit cases. So what happens if the two inputs are 0? Yeah, so the AND gate has two inputs and one output. What if the two inputs are 0? Well, the AND of 0 and 0 is 0. So the AND gate will require that in that case, the output should be 0. Okay, what if the inputs are 0 and 1? Well, the AND of 0 and 1 is still 0. So the AND gate is again going to require that the output be 0. And finally, what if the inputs are 1 and 1? Well, now the AND of 1 and 1 is 1. So the AND gate is going to require you to output 1. Now, where it gets interesting is, of course, what happens if the inputs are not pure bits, not just 0 and 1? What happens then? In essence, the same as with the NOT gate, namely, the AND gate does not care about the output. So, for example, in this case, if the first input is something that's not a pure bit, so something strictly between 0 and 1, and the second input is 1, then the AND gate is not going to care about the output. It's going to allow you to put whatever number you want here. But there is one more interesting case, which is what if I change this 1 over here into a 0? Okay, so in this case, something interesting happens, namely the AND gate, because there's a 0 over here, no matter what this value is, it already knows that the result should be 0. And so in that case, the AND gate is actually going to demand that you output 0. And so we call this the robustness of the gate. And it turns out that this is actually needed for the problem to be PPAD-complete, but I won't go into details about that. Okay, so let me just repeat that. The AND gate, if one of its inputs is 0, then no matter what the other input is, it's going to force you to output 0. If you didn't get this, you can forget about it. It's a bit of a technicality, to be honest. All right, the essence is, again, the AND gate works as before when the inputs are pure bits, and if the inputs are all garbage, then it's allowed to output whatever it wants. That's the executive summary. Okay, let's move on to the last gate I want to talk about, which is this weird new PURIFY-gate. So what does this gate do? So this gate has one input and two outputs. That's already a little bit weird. One input, two outputs. And what does it do? So if you give it a pure bit as input, it does something very normal. So if you give it 0 as input, it's just going to output 2 zeros. So it just creates two copies of the input, essentially. If you give it a 1 as input, it does the same thing, just creates two copies of the input 1. Okay, and the interesting part, of course, is what happens if you give it a garbage bit as input, namely something that's strictly between 0 and 1. What do you output then? Well, the only constraint is that the PURIFY gate requires you to output at least one pure bit, namely at least one of the two outputs, no matter which one, should be a pure bit, should be a 0 or 1. Again, the gate doesn't care about whether this is a 0 or a 1. It just wants to see a 0 or a 1 in one of the two outputs. So let's look at an example. Here we have a 1/3 input, and the two outputs are 1/5 and a half. Does this work? No, this is not okay, right? We have a garbage input bit, and both output bits, they're both garbage. They're both not 0 or 1, so that's not okay. But this will be okay. Okay, if this bit here is 0, that would be fine. Namely, the PURIFY gate here would be satisfied. And again, I can switch this 0 here to a 1. The gate is still satisfied. Again, what's the high level thing to remember about this purify gate? It's if the input bit is already a pure nice bit, then it just copies it, it just propagates it. If the input bit is a garbage bit, then at least it creates you one arbitrary pure bit. So you get something useful out of it. So now I'm going to move on to some examples, and then I'll pause for questions. All right. So let's go over the 3 twists that we had on the problem, because they allow me to show some things in terms of examples. So the first thing is that we allow the circuit to have cycles. Now, why is that important? Let's consider a circuit without cycles, like this one. Well, if the circuit doesn't have cycles, what you can always do is you can just go put some arbitrary value, like 0, for example, on all the source nodes of this circuit. And then you can just compute the gates normally as you would. And that will automatically satisfy all the gates, and you have solved the problem. So if there are no cycles in your circuit, then the problem is trivially easy to solve, essentially. Okay, so the cycles are what make this problem interesting and also hard. What was the second twist we had? The second twist we had was that the nodes can take values, any value between 0 and 1, not just the values 0 and 1. Now let's see, why is that important? Well, let's consider the following simple example. We have a cycle of 3 NOT gates. Now what happens if I'm only allowed to use 0 or 1 as values, not values in between? Then I might start by putting a 0 here, which means that I have to put a 1 down there. But then I have to put a 0 here. And then, of course, I have to put a 1 here. So it's quite easy to see that this circuit does not have a solution in that case. So allowing any value between 0 and 1 is important to ensure that the problem always has a solution. And always having a solution is very important if you want to use this if you want to show that this problem is PPAD-complete, it better always have a solution, okay? And so what is the solution to this example? If you allow any value between 0 and 1, for example, you could just put 1/2 on all of the nodes, and that will work, because if you remember the NOT gate, if its input is a garbage bit, like 1/2, then it doesn't care about its output. It can be anything. So 1/2 is fine as an output as well. In other words, if you put 1/2 everywhere, all the 3 NOT gates are happy with that, and they tell you, good job, you solved the problem. All right, so this is why we need any value between 0 and 1, and not just the pure bits. And the third twist that we had was that in addition to the standard gates like NOT, OR, AND, etc., we also introduced this purify gate. So why is that gate important? Well, let's imagine that we have this circuit here as an example that does not use any of the purify gates. It only uses NOT and AND gates. I could also have added some OR gates, that would have been fine. Now, what's the problem? The problem is that this is trivial to solve. I can just put 1/2 everywhere. Okay, if I put 1/2 everywhere, or 1/3, or 1/5, or if I put 1/5 over here, 1/10 over there, 1/2 over there, as long as I put garbage bits everywhere at all the nodes, all the gates are going to be satisfied. And as a result, it's trivial to solve the problem. Okay, so for the problem to be interesting again and to be PPAD-complete, you need to have this purify gate that kind of creates non-garbage bits out of garbage bits. So the last example I want to go over before I stop for questions is this, I guess it's a whole instance, a toy instance. So that has all the things that we need for the problem to be hard, like cycles, it has a purify gate, and I guess it's not completely trivial to solve. So if you look on the left here, you can see that essentially we have an odd cycle of knots again, and that will essentially force us to put garbage bits on this cycle. So we'll have to put garbage bits, for example, 1/2, but I could put something else. And then now, because of the definition of the purification gate, right, because it gets garbage as input, it means that, okay, this garbage is okay, but one of its outputs has to be a pure bit. It's not going to be this one, apparently, so it has to be this one. Okay, so this output has to be a pure bit. For example, let's put 1. And then you can solve the remaining instance. It's not too hard to see that, for example, putting a garbage bit here and here will work. But you can also put a 0 here if you prefer, and that will also be a solution like that. So this example is just meant to show that if you imagine that I give you a pretty big circuit like this, it's not going to be trivial to solve. There's no clear procedure that's going to allow you to solve this efficiently. You can imagine that the values over here could come back in here somehow with an AND gate, and you could have many cycles, and just an instance that's very complicated and hard to solve. And so this intuition is indeed correct. So this problem is PPAD-complete. It's as hard as any other problem in PPAD, even if you just allow the gates not and the purify gate. Okay, so maybe this is a good point to pause for questions. I'm not sure if I maybe let me do this. So yeah, if you have a question, just walk to one of the carpets so I can hear you. Otherwise, I can also come back for questions at the end. So the carpets are on the left and the right. I cannot hear you.
Can you hear me now?
Yes, now I can hear you.
What is the relevance of having the whole range 0, 1, rather than, for example, just like 0, 1/2, 1? Like, it seems like all non-integral values behave the same in this system.
You're absolutely right. I could just have said 0, 1, and 1/2, or 1/3, my favorite value between 0 and 1.
Okay.
That is correct. Now, the reason why I present it like this is I think it's easier when you reduce to other problems later to think of it as it can be any value between 0 and 1, but you're absolutely right. It doesn't change the problem. Just say we only allow 0, 1, and 1/2.
Okay, great. Thanks.
But excellent question.
Can you hear me?
Yes.
Yeah, hi. This was like a very nice introduction to this problem. Thank you. And I would just want to ask, like, can you give like a very brief intuition why this would be like end of line? Like, what I've been trying to thinking of the parity argument which goes off here, and I think it should come from the purify gate, but
Are you asking why this is as hard as end of line, or why is this in PPAD? Why does it reduce to end of line?
yeah, like a sort of end of line argument, like where's the parity to total existential argument going on here?
Yeah, so I mean, I think a very related question is why does this thing always have a solution?
Yeah,
Okay,
yeah,
right? Why does the solution always exist?
exactly.
And well, there's two answers to that. One answer is that in a few slides we're going to reduce this to finding a Nash equilibrium in a Polymatrix game, and that is known to have to always have a Nash equilibrium by Nash's theorem. But that's maybe not very satisfying. A more satisfying answer is that you can reduce this quite directly to Brouwer's fixed point theorem. I'm
That
afraid I don't have time to give the details, but there's a
I
pretty
thi-
direct reduction to Brouwer's fixed point theorem, and then that's how you would get to end of line, etc.
okay. I am now very curious to see that reduction. I'll try to think and then I'll take a look. Yeah, thank you. And
Great.
also,
Yeah, let me know.
yeah, and also get well soon. Yeah.
Thank you. Thank you. Um, all right. Maybe let me continue. So I think you can still see my screen, so I'll just continue. Interrupt me if there's anything wrong with the sharing. All right, so now we move on to the final part of this tutorial, which is Polymatrix games. So what are we going to do? We're going to prove a hardness result. So let me briefly introduce Polymatrix games in the remaining 10 minutes or so. So I'm just going to look at the simple case where every player has just two possible actions. Okay, so we have many players, n players. Each player has two possible actions that I'll just call 0 and 1, action 0 and action 1. And what that means is that the total number of pure strategy profiles is 2 to the n, because you have n players and every player has two possible actions. So overall, the number of pure strategy profiles is 2 to the n, which is a lot. And if you wanted to represent the payoffs for each possible strategy profile, that would take a lot of space. So Polymatrix games are a special class of games that have additional structure, which makes it possible to represent them in a much more succinct way. Okay, and they're also a very natural class of games, but I don't have time to discuss that, unfortunately. So what is the general idea? Why are these games succinct? What is the additional structure that they have? Well, the utility that a player gets from a specific strategy profile, it actually only depends from one-to-one interactions with every other player individually, and then you get a payoff from each interaction separately, and you just sum them up. So in a certain sense, you can think of it as some kind of additively separable utilities, where every term in this sum depends on one single player. Okay, and another way to think of it is as a graph, as a clique, where you have the blue nodes represent the players, and the red edges represent the small games that the players play. So, for example, we have two blue nodes here that represent two players, and there's an edge because they play a small two-player game, and that gives some payoff to this player. And then there's another game between those two players that also gives some payoff to the player, etc. So if you just focus on one single player, one single blue node, then the payoff that they get for a single action will depend on what happens in all of those 5 games with the 5 other players, but it will just be the sum of those payoffs. And this is what the added structure is in these Polymatrix games, as opposed to more general games where it would be more complicated than just a sum. Okay, that's the high-level idea. So this is a game, and what is an interesting solution concept for a game? Of course, it's a Nash equilibrium. And what is a Nash equilibrium? Where it's a mixed strategy profile where every player plays the best response. Okay, every player, given what the other players play, they play the best they can as a response to that. So by Nash's theorem, these Polymatrix games, like many other more general classes of games, they always have a mixed Nash equilibrium. And so a very natural question to ask is, can we compute such a Nash equilibrium in polynomial time? Or can we at least compute an approximate equilibrium in polynomial time? And of course, if you talk about an approximate Nash equilibrium, you have to define exactly how you define this approximate notion. And so for this tutorial, we just focused on this epsilon well-supported Nash equilibrium notion, which at a high level, it just says every player plays a mixed strategy that only puts positive probability weight on pure strategies that are epsilon best response actions. Okay, so they don't put positive probability on any action that is more than epsilon suboptimal. And I just want to mention that this is an additive approximation notion. We should think of this epsilon as being between 0 and 1. 0 means you have an exact Nash equilibrium, and epsilon equals 1 means you don't do anything. It's like a trivial, any strategy profile is a 1 well-supported Nash equilibrium. Okay, so we're interested in getting something for small epsilon if you're thinking about a good algorithm. And if you're thinking about showing good hardness result, then you wouldn't show it for a big epsilon. So let me just mention a very simple algorithm that achieves a 1/3 approximation. And what the algorithm does, it's very simple. It looks at your game and it just finds a player, if it exists, it finds a player who is always happy to play one of his two actions, no matter what the other players do. For example, the first action, which we call 0, find a player who is always happy to play 0, no matter what the other players do. And by happy, I mean that it will be a 1/3 best response. Okay, so if you find such a player, then you just fix them to play that action. For example, the 0 action, and you remove them from the game. And now you just keep doing that. As long as you can find such a player, you keep doing that. You remove the player from the game, you fix its strategy, and you move on. At some point, it won't be possible. There won't be any players like that. And in fact, it could also happen at the beginning of this algorithm. There might not be any player like this. So then you have a game where no player can play a fixed strategy all the time and be happy. And what you do then is even simpler. For all the remaining players, you just have them mix uniformly. Namely, you tell them, okay, play your two actions with probability 1/2, 1/2. And that's it. That's the algorithm. Eliminate people who can always play some pure strategy and be happy, and the remaining ones have them mix perfectly 1/2, 1/2. And by a direct computation, you can show that this always gives a 1/3 well-supported Nash equilibrium. Now, this is a pretty naive algorithm, and surely you must think there must be some way to compute a better approximation. But it turns out that no. So we can actually show that if you want anything better than 1/3, that's going to be PPAD-complete. Okay, so this is like a tight threshold thing. And let me just mention that using the previous tools that are this generalized circuit problem, it was possible to show already that there must exist some constant where the problem becomes PPAD hard. But using this pure circuit problem, we can now show that it's actually just below, anything below 1/3. So what is the proof going to be? The proof is just going to be a reduction from this pure circuit problem that we saw earlier to the problem of computing an approximate well-supported Nash equilibrium for any epsilon less, strictly less than 1/3. So again, what is a reduction? Well, we're given an instance of pure circuit. We have to construct in polynomial time a polymatrix game from that instance. And the idea, I'm just going to do a high-level thing because we don't have much time. We're going to create one player for each node of the pure circuit instance. And every player is going to have two actions, 0 and 1. And they're going to represent the bits, the pure bit 0 and the pure bit 1. And of course, the players are allowed to mix. And mixing between 0 and 1 will exactly represent values between 0 and 1. So if this is your pure circuit instance that you start with, then you're going to create one player represented as a blue node here for each original node in the pure circuit instance. So one player for each of them. And then you're going to define those games between the players, those small two-player games, so that you implement the constraints of the gates correctly. Okay, and this is going to look, it's going to have a very similar look to the original graph because you're. So just going to take 2 minutes on the gates and then we'll be done. So what you need to do in such a reduction is just show how you can implement the gates from the original pure circuit problem. In other words, how you can enforce the constraints that you have in the original problem. And so if you have a NOT gate like this, there will be a corresponding player for the input node and a corresponding player for the output node. And what you need to do is just define the game that they're playing between them, okay? And I've put an arrow pointing from U to V here to indicate that V cares about what U plays, but U is actually not going to care about what V plays. And what we want now is just to enforce the NOT gate. What does that mean? Well, it means that if the top layer who corresponds to the input node plays 0, then I want the output player to be incentivized to play 1 at an epsilon well-supported Nash equilibrium. And if you look at this table that represents the payoffs, this is the game that we construct at this edge. Well, if U, which is the top node, plays 0, that means that we are in this left column. And the payoff for the bottom player, V, is 0 if he plays the top row and 1 if he plays the bottom row. So he will play the bottom row, which corresponds to 1. Okay, and by the same argument, if the top player plays 1, the bottom player will have to play 0, etc. Note that we don't need to verify anything else, because if the top player mixes between 1 and 0, then the NOT gate doesn't care about what happens, so we don't even need to check anything else. So essentially, we do the same thing for the AND gates. I'm not going to go over the argument. Again, you define small games between the players that exactly implement the constraints of the AND gates as defined in the pure circuit problem. And this construction actually requires it to be right below 1/3 to work. And the same for the purify gate. You just construct the local games that are going to ensure that you exactly implement the constraints of the purify gate. Okay, and that's it really. So I'm not going to go into detail about why this holds, why if you do the computations, you do implement the constraints correctly, because that's not so interesting. What I wanted to tell you is mostly just about this pure circuit problem that I think is the simplest one we know at the moment to prove PPAD hardness, and the general idea of a reduction, which is just find what your nodes are, find how they implement the value, and then just ensure that you implement the constraints of the original pure circuit problem. So let me just finish by doing some advertisement for a workshop, which is taking place next Monday. If you're not planning to be in Paris next Monday, don't worry. You can attend it online, and attendance is free. You can just register on the website, and you'll hear more about all this TF&P stuff there if you want. All right, that's all from me.